Now, I'm very excited to present our headliner, our main event, Dr. Michael Caligiuri. Dr. Caligiuri is the president of the City of Hope National Medical Center in Los Angeles, California. He also holds the Deanna and Steve Campbell Physician-in-Chief Distinguished Chair. Prior to his appointment to City of Hope, Dr. Caligiuri was the CEO of the Ohio State University James Cancer Hospital and director of OSU's Comprehensive Cancer Center. During his time as the Cancer Center director and hospital CEO, Mike oversaw the construction of the third largest cancer hospital in the US and recruited over 300 physicians and scientists to the Ohio State University. Full disclosure, I was one of his recruits. Mike has a very long list of accomplishments, and so I want to yield most of my time to him for his talk. But I just want to quickly say, that Mike is your prototype physician scientist, and him and his research group has done a lot of the seminal work on NK cell biology and therapy for liquid and solid tumors. And with that, please welcome Dr. Mike Caligiuri as our keynote speaker. And the title of his talk today is The Cancer Journey and Lessons Learned Along the Way.
Okay, great. Thanks very much. And thanks for the kind introduction. I will share my screen here and we can get going. Thanks for the opportunity to speak at this Research Day. It's a real honor for me to do so. I'm very grateful for the opportunity. I want to start by just listing a few disclosures. As you can see here, I'm on the scientific advisory boards of a few companies, and I co-founded a company which I'll chat a little bit about a little later. I wanted to start, given that we're in Ohio, with an Ohio story, which is cute. A while ago, my son went in fourth grade, and he's now like 30 years old, asked me what a high-impact journal was. And I told him that it was a journal that, a lot of people around the world read, that if you got an article published in a high-impact journal, hundreds and hundreds of people would read that article, and it would have impact in the field. So his name is the same as mine. And I'm going to fast forward to another story. A kid walked in my lab when I was at Ohio State, big kid, and wanted to work in the lab. He had a 4.2 GPA in molecular genetics. And it turns out he was the quarterback in the Ohio State football team. And he worked in my lab for the entire year of his senior year when he was the starting quarterback, ended up winning the national championship. And Sports Illustrated wanted to do an article about him, and they interviewed me for the article. So my name is in the article several times. So my son came home from school one day and said, "Dad, this is a high impact journal." He said 23 million people read this, and my name's in it. So most famous person to work in my lab was this guy, Craig Krenzel. So really, really bright guy. So we're going to talk today about NK cells, and we're going to talk a little bit about my cancer journey. This is kind of a hybrid talk. I normally spend 45, 50 minutes talking about my laboratory love, which are natural killer cells. But Quentin asked me to also speak about, as you know, my journey along the way, starting from early in my career to where I am right now. And so I'm pleased to do that, and hopefully we'll provoke some questions from the junior folks in the audience. We'll talk about the role. So natural killer cells are the third type of lymphocyte in your body. Think of the T cells and the B cells. We'll talk about how NK cells develop, where they develop, why it's important to know this, and what are some clinical applications of the NK cell receptor biology. So back many, many years ago, 30 at least, this is what was known, was that if you took a CD34 positive cell and you put it in culture with IL-2, it would make natural killer cells defined by the CD56 antigen. And the question was, is this the real cytokine responsible for NK cells? Because it's only made when T cells are activated in very tiny amounts, yet you have billions of NK cells circulating in your blood every day, 3 times as many as B cells. And sure enough, when the genetic disruption studies were done, knocking out IL-2 or IL-2 receptor alpha, you still had NK cells. So clearly it wasn't required for NK cells. On the other hand, if you knocked out the other 2 chains of the IL-2 receptor, the beta chain and the common gamma chain, you got no NK cells. So that told us that something that wasn't IL-2 and didn't use the alpha chain, but did use the beta and gamma chain, was responsible really for the production or development of NK cells. And so here's that heterotrimer, the IL-2 receptor, and you see the alpha, beta, and gamma chains. And here are the 2 chains, the beta and gamma, which are required for NK cells. And the reason these are required is that another cytokine had been discovered, interleukin-15, which binds to its own alpha chain on antigen-presenting cells and presents IL-15 in trans to the beta and gamma chains that sit on the surface of the NK cell or the CD34 cell, and then drive it towards NK cell development. And so if you, in fact, take IL-15 instead of IL-2 and you put it in the presence of the CD34 positive progenitor cells, there you get your CD56 NK cells. And you see that they're all CD56 bright on this histogram here. And these are the earliest NK cells that come out of the blood. They actually only represent about 1% of your blood NK cells. Most are CD56 dim, but they develop a little later, as I'll explain. So we were interested in finding what's the CD34 precursor and for IL-15. I should mention that when you knock out IL-15 or IL-15R alpha, mice lack NK cells, confirming that this is in fact the real lymphocytotrophic hormone for NK cells. So how do we find the subset of 34 cells that represent the precursor of NK cells? Well, we divided them up into 3 populations, as you can see here, 1, 2, and 3. And then we put each of them in the presence of IL-15. And what you notice is that only the third one, this CD45 RA positive, but 34 low, this is where the precursor lied, because in the presence of IL-15, we could drive it to the CD56 bright NK cells. I should say that none of these cells expressed beta gamma receptors sufficiently high enough to detect, and that's why we had to go to this functional assay. So to learn about how and where these cells develop into NK cells, we did a lot more phenotypic analysis of the CD34 positive cell. And to make a long story short, what we found is that this third population had very high surface density expression of L-selectin and beta-7 integrin. And these are expressed on cells that traffic to lymph nodes, secondary lymphoid tissue, spleen, tonsil, lymph nodes. And up until this point, no one had ever described a CD34 cell in a lymph node. But this phenotype told us these cells are leaving the bone marrow and trafficking to lymph nodes. And so what we did is we went to lymph nodes. First, we took a CD34 column and we ran peripheral blood through it. And you see all 3 populations of CD34 positive cells coming through. But when we did the same thing with lymph nodes, you see only the 34 population was found. And in fact, this was the first description of CD34 positive hematopoietic progenitors found in situ in the paraphilic T cell rich regions of tonsil and lymph nodes, et cetera. And further, when we then took this population and placed it into interleukin-15, you can see that it drove this population that was found in the lymph node to the CD56 bright NK cells, as shown here. So that led us to believe that maybe NK cells don't develop in the thymus and don't develop in the bone marrow like T cells and B cells, respectively, but develop in lymphoid tissue, and no one knew where human NK cells develop. So our next question was, well, do these cells naturally exist in a lymph node? And in fact, you can see here that they do. Again, in that parafollicular T cell rich region, here you see the CD56 bright NK cells. So, okay, now we had CD34 and the end product CD56. How does this process occur? So a lot of work that I'm just running through using three markers, CD34, c-KIT, and CD94, we were able to show that when cells first start with CD34, then acquire c-KIT, then lose 34, and then acquire CD94. And if we look at CD56 in this population, all found within lymph nodes or tonsil, what we see is the actual development of NK cells going from CD56 negative to dim to brighter to the bright. And so we've gone on to focus on this in our laboratory, having discovered that NK cells develop in secondary lymphoid tissue. We've focused on this over the next 20 years, and I'm summarizing that in a single slide. So now what we've determined, both at the surface phenotypic level, but also at the molecular level, describing the transcription factors, et cetera, and also co-discovering innate lymphoid cells, that there are these 6 or so steps of NK cell development, and they occur in a very consistent pattern, all happening in a dynamic fashion within the parafollicular rich T cell regions of the parafollicular T cell rich regions of the lymph node, with dendritic cells presenting the IL-15 to move this whole process along. Now, why is this important? Well, we've learned from B cells and T cells that very often during these processes of lymphoid differentiation, one gets malignant transformation. And I'll just show you one example of that. Here is a stage called stage 4A. And you can see it's as the precursor of NK cells transitions from 94 positive to NKp80 positive. And right at that point, there's this unique population here called 4A. So when you look in blood, for example, or bone marrow, you see no 4A cells. But if you look in tonsil, secondary lymphoid tissue, or lymph nodes, secondary lymphoid tissue, there they are. Well, there's this type of lymphoma called EBV NKT cell lymphoma, a devastating, deadly, also called midline lymphoma. No known therapeutic options for patients who get this very, very disfiguring cancer as shown here. Well, if you take patients who've had this lymphoma and you look at 4 different patients here, you're looking at blood, bone marrow, peripheral blood in another patient, and central CSF, because a lot of these patients metastasize to the brain. What you see here is all of these patients, the malignant cell is that unique stage 4A intermediate NK cell. And so seeing this normally and this in the malignant counterpart, this has allowed us to do an extensive molecular, genomic, epigenomic analysis of these. And we just published this in Blood Cancer Discovery, showing that this tumor, this EBV NKT cell lymphoma, is the most highly methylated tumor of all tumors studied thus far. And in fact, when we give a demethylating agent, such as 5-AZA, we can differentiate this malignant tumor in vivo, setting us up for some real therapeutic options for patients with this lymphoma. So there's merit to some of this, studying the developmental biology and discovering where and how such lymphoid cells develop. So now let's try to get inside the mind of a natural killer cell. Here's an interesting picture where you might think the NK cell is here, but in fact, it's the lower, smaller cell here. And what it does is it releases granules and gamma interferon, and it punctures holes in the cytoskeleton of the tumor cell, leading to a complete deflation of that cell. And importantly, you see that the NK cell remains alive. So we've shown, and others have shown, that NK cells kill serially. So it not only could kill this cell, but if you add more tumor cells, it will kill again. So it's a serial killer, in fact. So to use a clinical example that we study as well, let's talk about glioblastoma. This is, as most all of you know, an extremely deadly cancer. You can see the survival's on the order of 14 months, of course, much shorter when virtually 100% of patients present with stage 4 and relapse inevitable within this time frame in which you got a completely incurable tumor. So radiation, chemotherapy, surgery, none of resulted in curable disease. And so many folks are looking at different opportunities. One of the things that we look at is oncolytic viruses. And in fact, herpes simplex virus type 1. This is a neurotrophic virus. So Mother Nature has manufactured this virus so that it looks for, binds to, infects, and kills neural tissue. Many of you have had herpes infection of the mouth, et cetera. You know, it's actually binding neurons, and certainly you've heard of herpes encephalitis, often occurs in immunocompromised people or in infants prior to developing real immunity to this. And so what you can do is you can alter the genome to take out the pathogenic components of this that lead to vast encephalitis and put it under control of promoters that are only found within the glioblastoma, and then infect the patient. It's taken up and it's activated only within the glioblastoma cells. And I'll show you an example of how an oncolytic virus can work in vitro. So here what we're looking at is glioblastoma cells in vitro. We're going to add the virus that'll come in here. And you'll see, again, being a neurotropic virus, being oncolytic, it'll infect, it'll replicate, it'll spread, and then finally, it will lyse. So just beautiful in vitro work that you can see here. That's the beauty of the system. And the reason why we all don't die of overwhelming primary infection of herpes is because our NK cells form a first line of defense against herpes virus. That's why we're not. These cells can attack the virus within minutes of entering your body, and in fact, there are multiple examples of people that lack NK cells that have severe, overwhelming herpes virus infections, as shown here. So that's the good news. The bad news is if you're trying to give viral therapy, and we've shown now that NK cells really impede this whole process. So that's actually, we published this again, just to run through this. We published that when you're trying to give viral therapy, which can work very well, NK cells rush into the CSF and to the central nervous system and will block this. And it's illustrated in this cartoon. So now we're in vivo. Now we've got normal neurons, setting of the glioblastoma. And so again, we have our virus, oncolytic neurotropic virus, comes in, starts its process of replication. But before it can get on to spread and lyse, NK cells come in, recognize herpes virus, and in fact prevent it from doing what we want it to do therapeutically. So our lab went on to discover how in fact this process occurs, looking at over 90 different molecules expressed by the herpes virus, and understood what it is that NK cells are seeing. And we've gone on to devise a number of viruses now with genomic manipulations that can prevent this quick attack. And I'm just showing you one example of that. In one case, what we do is we've encoded the herpes virus to express the ligand, which binds to an inhibitory receptor on NK cells, basically a stop sign that says when you go to attack this GBM, the GBM is filled with the oncolytic herpes virus, but it also encodes an inhibitory ligand, which sits now on the surface of the GBM. that binds to the NK cell, the NK cell binds to that ligand, inhibits it from doing its killing, and allows the virus to replicate, spread even better, and ultimately be killed. And in fact, in our in vivo models, just to kind of come to the quick, you can see here that with administration of this virus compared to just the naked herpes virus, we get profound improvement in the survival of the mice. This is both in human immunodeficient models as well as mouse immunocompetent models. So we've gone ahead now, and we're actually furthering this. You just heard a very nice lecture on CAR T cells. We've gone ahead and started to make CAR NK cells. In this case, we've got a CAR NK cell that encodes EGFR. EGFR is found selectively on GBM and not in normal brain tissue. It's found our CAR can recognize both wild type and the EGFR mutant V3. And in fact, what we've shown, and I don't have time to show you here, is not only is it successful in killing, but with our genomically altered viruses, it gives an additive effect of curative therapy. So we've started to move into the clinic with these modalities. We just finished treating about 52 patients with the naked virus that we use, stripped of its pathogenic properties, able to infect under a tumor-specific promoter, replicate, and lyse. And we've had some very nice results. This will be presented and published at a later date. We just completed this study. But of course, now what we're doing is we're looking forward to continuing the next phase 1 with one of our genomically altered herpes viruses and ultimately combining it with our CAR NK cells. Now, we've just talked a little bit about NK cells that see virus, and I thought I couldn't tell you much about how it works. It can work before there's any antigen-specific immunity in the body to herpes. In other words, your first primary herpes infection, NK cells are able to kill it through a very unique receptor mechanism that we described. But the other sets of NK cells floating around in your body don't see virus, but rather see tumor. And we subsequently discovered that NK cells that see tumor express PD-L1. You know of PD-L1 as the ligand which binds to PD-1 and blunts T cells. And you know of anti-PD-1 and anti-PD-L1 antibody therapy as being revolutionary in the treatment of a number of tumors, perhaps most importantly lung cancer, where we've gone from moved it in some cases up front before chemo and radiation therapy with startling results. Well, PD-L1 is also expressed on NK cells when it sees a tumor. And if you think about it, it makes sense, right? A tumor has PD-L1, but it wants its neighbors to also express PD-L1 so that it can bind to PD-1 on T cells and also blunt them. So it kidnaps the NK cell and expresses it. What we discovered is that if you have anti-PD-L1 attaching to this antibody through a P38 NF-kappa B pathway, it actually activates the NK cell further. So what we found is that the mechanism of anti-PD-L1 antibody in tumors that don't express PD-L1 but still respond to anti-PD-L1 is in fact due to the PD-L1 that's expressed on the NK cells. And in this case, the anti-PD-L1 is not so much blocking the NK-T interaction or the tumor T interaction, it's activating the NK cells to kill. And we published this in Cancer Discovery using various knockout models. So what I want to show you now is just some evidence of that. Here's an NK cell. We expose it to a tumor, and you see at first the NK cell is killing. Here's the release of granules by this marker. Here's the release of gamma interferon at this marker. And this is all happening within 2 or 4 hours. But what you see is later on, around 16 hours, look what the NK cell does. It upregulates PD-L1 on its surface. It says, I'm the guy that killed those tumor cells. And in fact, that's that PD-L1 on the surface marks a very, very potent NK cell that can be further activated by an anti-PD-L1 antibody like atezo. So here's separating out the NK cells in a patient that's seen with a tumor, and you see here's no PD-L1 on the surface or PD-L1 negative. Here's PD-L1 positive. So these PD-L1 positive NK cells have higher release of granules and higher gamma interferon in the PD-L1 positive. But further, when you take them and you add an anti-PD-L1 antibody, such as atezo, as shown here, you go from 15% granule release to 60% granule release, or 7% gamma interferon to 21%. So threefold, fourfold increase using anti-PD-L1 antibody. So as a consequence of these findings, we've started to look in tumor models. When you give NK cells through the vein in either mice or human, these are labeled NK cells, they traffic to the lung and stick in the lung because there are vascular adhesion molecules which the NK cells bind to. So lung cancer might be an ideal tumor to give these activated NK cells to. And so when we do that, as shown here, you can see a sniffling of increase in survival. This is just vehicle, and this is the NK cell. This is the mice that got NK cells. And this is a tumor. When it turns red, it's near lethal. And you can see just by virtue of the color and then by the survival that there's a difference when you put these PD-L1 positive tumor reactive cytokine killer cells into the mouse. And this is a human tumor. These are human NK cells. But further, we've engineered the NK cells to secrete IL-15. And IL-15, as you know, activates and keeps the NK cells alive. And it also can activate and keep CD8 T cells alive. And you remember in your last talk, our presenter talked about T cells dying off early and these patients not doing well. So look what happens when we put in our activated NK cells, engineered to express IL-15, and then we put some T cells in, and then we add atezo. Now look at what's happening in terms of the tumor model. Almost complete lack of progression, or actually diminution of the progression with this combination. So as a consequence of this, we've gone ahead now and manufactured these PD-L1 positive NK cells in our GMP facility out at City of Hope. And we use umbilical cord blood, take it, stimulate it with a feeder cell line to start growing rapidly, transduce it with a retrovirus expressing soluble IL-15, grow it up further, and then can cryopreservate it. So these are allogeneic, off-the-shelf, ready-to-go cells that we can now expand in a commercial sense. And so we've moved now into the clinic with this genetically engineered NK cell, starting first without and ultimately will be given with atezo. We're now on our fourth or fifth patient, the study going on at City of Hope in collaboration with Cytomune Therapeutics. The idea is get to a maximally tolerated dose and then add the atezo in patients with resistant or refractory lung cancer to see if we can't get further than we have with chemo, radio, and the immuno-oncologic effects thus far with anti-PD-1 or anti-PD-L1. So that's just some of the work that we're doing. We have a lot more CAR NK cell work going on in pancreatic, AML, et cetera, that we don't have time to address today. I want to get to the second half of the talk, which I promised, and just really talk a bit about my journey, both as an oncologist, as an immunologist, and as having the opportunity to lead at various organizations and where we've gone. So first issue is where do I come from? Just a little bit about my background. These are my four grandparents who came independently to Buffalo, New York, where they all arrived between 1913 and 1920. Not only poor, but highly uneducated. And a collective education of 8 years, all laborers. This on the right were your migrant workers, as my dad was a migrant worker. And this is a presser in a textile factory. steam presser, and my grandmother worked in a canning factory. But they got here, they were hardworking and able to, ultimately each buy a home, which, is key to developing in this country and something we denied our African-American citizens for far too long in this country, tragically, and need to pay for that. But they had the opportunity to acquire a home and have families and married. And my parents came along, met in Buffalo, and then brought us along. This is my sister and I. Very Catholic family, as you might be able to tell from these Halloween costumes. I think my mother was trying to send us a less than subliminal message. And if you don't believe that, we then went on to have 10 children. So as is typical of the Catholic families in those days, all raised in Buffalo, New York. And then my parents, whatever, several years later, 10 years later, this is my graduation from medical school. And the same year I had the opportunity to meet the Pope, having living in Rome, and I studied some art history in Rome, had this tremendous opportunity. And I used my story with the Pope to meet and pick up my wife, who I met when I was an intern at Brigham Women's Hospital, Ani, who's originally from Puerto Rico. And here we are, 40 years later, still having a great time. So we went on to have 3 kids. As you can see here, I was at this time a new assistant professor at Roswell Park. And these are 20 years later, our kids. And finally, this investment begins to have its rewards when the grandchildren start arriving, because any parent can tell you raising kids is extremely difficult. But when the grandkids come, life is good. So that's a little bit of background on myself. What inspired me to pursue a career in cancer medicine? Interestingly, I was not interested, didn't know cancer medicine very much. Wanted to be a pediatrician working in the inner city of Buffalo, where I worked, and did my pediatrics rotation. Came across what turned out to be a burned out physician, really turned me off to pediatrics, although he shouldn't have, but I didn't know what burnout was. And this person was just miserable and rude. And I thought, well, this must be the profession. So I was kind of stumbling around and was on a renal rotation and came across a patient who was rejecting his kidney. He had had a kidney transplant. And I'd always liked immunology. It was the one basic science course that seemed to make sense to me. I didn't like science. I was a humanities major in college, didn't like science in college at all. But immunology really made a lot of sense to me. And then I was on the wards and this guy's rejecting his kidney, and my resident told me, it's the T cells thinking the kidney is a virus, and because it's foreign and these HLA molecules. And what I want you to do is go get this experimental medicine over in the heart transplant program. It's called cyclosporin. So you're going to get that medicine. You're going to give it to this guy. Of course, no IRB. This is the days if you just kind of got these things going. And you're going to measure levels on the person all night. And we're going to see to it that this drug will quiet down his T cells. And maybe the rejection of the kidney will stop. And maybe he will be able to urinate, because when he came in, he came in because he was urinating and was not urinating and didn't know why. And turned out it was his kidney, his transplanted kidney was being rejected. So I did that, got the cyclosporin, got it administered, took the levels, was in the hospital basically 2 days nonstop. And sure enough, after about 2 days, the guy started to urinate. And the whole thing just blew me away. It was like a laser beam. I couldn't believe that, okay, so we knew a little about immunology. We have this drug and we can give this drug and it attacks the problem. And if you attack the problem with the drug, maybe the guy his kidney can work again. So I said, I have to do this. I have to be a transplanter. I said, oh, okay, well, you got to be a surgeon. Didn't really like surgery either. So I said, is there anything else you can transplant? I said, well, we're just starting this thing. It's called bone marrow transplant. We don't do it here at Stanford Medical School, but, you can maybe do an away rotation. Sure enough, they were doing it at Roswell Park for my Buffalo days. So I went back to Buffalo, did 2 months of bone marrow transplant, and I heard Koen Van Biezen in the audience there, and I just probably like him, fell in love with it. Couldn't believe you do this. And I kind of figured out along the way that you do this for cancer. So that's when I got interested in pursuing cancer. I said, okay, well, if I want to be a transplanter, I have to learn about cancer. And then learned about cancer, got very, very interested in that as well. Leadership is a different story. You start out having no idea whether you do or do not possess any of the skills necessary to become a leader. Fortunate for me is I had an amazing mentor, which several people in the audience know, and her name is Clara Bloomfield. And so went to med school. I went to SUNY Buffalo for college. I went to Stanford for med school. I went to the Brigham Women's Hospital for internal medicine. And then I went to the Dana-Farber for oncology and started on the faculty there and realized I couldn't afford it. I had one child, two children, one on the way, and it was just way too expensive to live there. And at that time, this woman, Clara Bloomfield, called me and said, "My name's Clara Bloomfield. I just left the University of Minnesota. I become the chair of medicine at Roswell Park. And I heard you're from Buffalo. And I know your laboratory mentor, Jerry Ritz, well, and I'd like you to come here for an interview." And so I went there and she just, basically said, "What do you want to do?" And I said, "Well, I kind of always wanted to be a bone marrow transplanter. I still do. I love it. But I've been in the lab for 2 years. It's required by the Farber. And I'm kind of falling in love with this cell. It's called an NK cell." Well, she really needed somebody to build her transplant unit. She said, "I'll tell you what, you come here." And she almost tripled my salary overnight from the lowly Harvard salary to a decent salary. The cost of living dropped in half. So financially, it was like, this could work. This could keep me in academic medicine. And she said, "You build me a transplant unit." Roswell's unit had closed down. They had had an aspergillus outbreak years earlier, and they didn't have a transplant unit anymore. "So you build me a transplant unit, I'll give you a lab, I'll give you a startup, I'll give you a technician for 3 years. And if you can get a grant, you can keep going in the lab. You see transplant patients, you get this going." So I was like, "Oh my gosh, great deal." So we picked up our bags and we moved to Buffalo, New York, had a great time. But the most important aspect of that, two things that I would tell people in the audience. One, my mentor, Clara, remained my mentor until her death. And actually for the last 10 years, I became her boss, but she still mentored me on a weekly basis, as Quentin, Ted, and Melissa certainly know, and maybe Kuhn knows as well. But the other was that, the Dana-Farber really didn't need me. They had no use for me. As soon as, I was gone, there was someone else there to, take my place. And it was going to be years before I got my own lab, my own tech, my own startup. If I was fortunate to get 1 or 2 R01s, that was really hard to do as a new investigator. Could get a K award, but you'd have to stay in someone's lab. And so one of the things I learned early on, and this is important for, I think, people training and looking for opportunities, that opportunity is inversely proportional to what's in place. If, I wanted to go at that stage, I was at Roswell Park and I wanted to go to the Dana-Farber. Dana-Farber was chock full of everything you needed. My ability to create impact there, to even have the opportunity to lead, would have been zero. On the other hand, leaving the Dana-Farber and going to Roswell Park with a new chair of medicine, she had a lot of resources to start recruiting. I was their first recruit. The opportunities for me, whether I understood it at the time or not, were huge. They were unlimited in anything I wished to do. And she gave me 2 right off the bat: build the transplant unit and get it running, recruit. And she put me in charge of recruitment. And oh, by the way, you can have your lab and get going there. So without even knowing it, I got opportunities to lead, led the development of the transplant unit, quickly recruited people more senior than I to run it, got the opportunity to lead recruiting. So there I was, this new assistant professor, 1990. We recruited about 25 people over the next 5 or 6 years, which, is a pretty good clip, about 5 a year, and really, really grew it. And I watched Clara work on who she wanted to recruit, the type of person, and just phenomenal learning experience. And then I got to start my own lab. And so it became leading students, leading my technician, presenting my material, it being my material and not my mentor's material from my former postdoc at the Farber. So all of those things happened because this place needed people. And I always tell people that, look for the opportunity. That's where you're going to get the opportunity. Look for what's in place. If everything's in place and you're the cherry on top, unless you're being recruited as that leader, your opportunity to showcase yourself, even inadvertently as a leader, is really, really limited. On the other hand, you go to a place that they're looking for people who want to get things done. And if you show that you have the skills, it's likely that your mentor will notice that. And that's what happened to me. We were successful at recruiting. We were successful in building the transplant unit. My lab became successful. It grew precipitously. And what I learned from Clara, watching her as a leader, she really put down her own career. I mean, as Kuhn can tell you, Clara Bloomfield at that point was the #1 authority in acute myeloid leukemia in the world. And she set the whole WHO classification. And she really told me, she said, for 3 years, I'm not giving a talk. For 3 years, I'm not going to any meeting except CALGB, where she was in charge of leukemia, correlative science. And so I really saw her, I was like, wow. I mean, invite after invite, no. She had a new job to do. And, you know, from that, I learned that leadership can be defined as a single word: selflessness. If you're not ready to give up what you're doing to help others, you're not ready to be a leader. You'll meet people that go into leadership, take the leadership position to get the big office, to get the higher salary, to have the power, not a person you want to work for. You want to work for a person that devotes themselves to helping others. And that's why they're ascending to leadership, because in their mind, this is the time to do that. I've done enough for myself. I've had the help from my mentors. Now it's time for me to take over and lead for others, mentor others, move others along. Get my greatest satisfaction is to recruit people better than me and see people transition into physicians and scientists better than me. That's what I learned from Clara Bloomfield. Unfortunately, Clara passed away 2 years ago. I had the honor of writing a brief piece about Clara and cancer research. I'd encourage you to take a look at it for a brief synopsis of her amazing life and what an incredible human being she was. So after about 7 years, the top leadership at Roswell just wasn't working out for us. They changed leaders, and they went from someone who was very scientifically grounded, interested in translational research, to someone who's more interested in, things that didn't interest us, trying to grow the business, practice plan, and that need to do that. I ended up doing that in my next position, but always in the context of remember who you are and what you do. In our case, we do academic medicine, discovery-based research, moving things from the lab into the clinic, early phase, later phase clinical trials. And so things got a little lost at Roswell at that time. And it really became time to leave. I thought I'd be at Roswell Park the rest of my life. I'm from Buffalo. My wife loved it. It was no problem for us to stay there. But professionally, it really wasn't going to work. And I remember people saying, well, Mike will probably never leave. He's from here. And I was like, wow, I'm going to be taken for granted. And really started to look around. And Clara felt the same way. And we decided to move together along with Clara's husband, who's a very renowned geneticist, Albert de la Chapelle, who's done a lot of work with Sandy Markowitz, for example, Case, very dear colleagues. So sure enough, remember what I said, opportunity inversely proportional to what's in place. Ohio State was looking for new cancer center director, new head of hematology and oncology. They had gotten probation on their NCI core grant. They had 3 years of funding instead of 5. It was considered phase-out funding. They were in bad shape, and they needed people. And so we had opportunities at MD Anderson. We had opportunities at Memorial Sloan Kettering. The three of us, Albert de la Chapelle, Clara, and myself, we decided to go to Ohio State. And I remember asking Clara, why are we going to go there? And she said, because that's where I think the greatest opportunity is. And you think about it, how do you create impact at a place that's chock full of people? It's difficult. So we came here and, as an asset, largest public university in the country, had a very comprehensive health sciences campus, which at the time, the dean who was recruiting us was the late Bernadine Healy. Had a comprehensive cancer center that was in trouble, but it had the designation, and it had this freestanding cancer hospital. And the CEO of the freestanding cancer hospital, Dave Schuler, was also recruiting us. He was partnering with the dean to get us there. I thought, well, this is very interesting because it's a matrix center. It's a university, but they have kind of a Roswell-like campus as well, of its own cancer hospital, which was losing lots of money, but it was standing at about 30% occupied. Well, this is 1997. One of the things we wanted to do is to rebuild the Comprehensive Cancer Center. And you got to look at, when you're doing something like this, you have to say, what is it that I have and what is it that the world needs? And so what we had at Ohio State was this large university with like 14 different colleges. And so what we did is we started to build membership to the Cancer Center, not just in the cancer area, not just in the medical center area, but throughout the entire university. Look at all of these various colleges that we had members in. I mean, sure, medicine, nursing, dentistry, et cetera, but, public health, pharmacy, arts and sciences, vet med, law, engineering, business, food, agriculture. We ended up having a crops to clinic program. Further, we didn't limit it to the campus. We included Nationwide Children's Hospital and Cincinnati's Children's Hospital because Cincinnati didn't have a comprehensive cancer center and the Children's Hospital wanted to be part of ours. Fine. So as was mentioned, we recruited over 300 people. That included Ted, that included Quentin, that included Miss Melissa Childress, and many others, probably several others in the case system now. And really were able to grow this baby in a big way. And we looked at, well, who do we have? And then we formed our programs around who we had versus saying, well, these are our programs and not being willing to change them. We were able to very quickly, because of Clara's reputation, recruit a lot of people into leukemia, and because of Albert de la Chapelle's reputation, into cancer genetics. So we kind of built on our strengths as quickly as we could. Well, as I said, when we got there, it had been on probation and was due for review in 1997, 3 years phase-out funding. They received a very good. Clara came in as the cancer center director. I was head of HemOnc. And she got us to she got a delay, and we were able to compete in 99 and got us to a solid excellent. And then after that, Clara said, Michael, I'm done with this. You need to take over now. It's time for you. And she went and talked to the president of the university and said, this is the guy that should be leading the cancer center. I don't think there was a search or anything. It was just a presentation of sorts I cut my deal. And I became the cancer center director. I was associate director for clinical at that time, and without much fanfare. And then was able to continue to grow it. Of course, I had Clara as my mentor. We went on to receive an exceptional. And then we went on actually in 2015 to be the first matrix center in the United States to ever receive a perfect score from the NCI in the history of the Cancer Centers program. So quite a nice accomplishment for what an amazing team that we had. Having recruited, like I say, over about 350 people. And then the opportunity came to lead the cancer hospital and really have a single leader over both the cancer center and the cancer hospital. And so did just that, became the CEO in 2008. And as you could see, we went from negative making money about the next 4 or 5 years that after we arrived, we didn't make any money at all. But eventually we started to make money. And part of my deal was we completely filled this cancer hospital. I think it had like 90 beds. And part of my deal in taking over in 2008 was that the university committed to a second cancer hospital. And you can imagine how challenging that is with all these different colleges, institutes. You already have a cancer hospital. Now you're angling for a second one. But we really felt that we had a formula that could produce revenue for the entire university. And in fact, you can see here by the time I stepped down 10 years later, we were about 350 million. And the cancer program was only using about 70 of that. So the rest of the money, after we built up days cash on hand, went to the remainder of the university. It became the highest generating resource of revenue in the entire university, including the athletic department. So it became a source for everyone. So it turned out to be for the greater good. And of course, it's like a 320-bed cancer hospital, which we're quite proud of. I want to stop for a minute and acknowledge the chief operating officer, Jeff Walker, who then recruited Melissa Childress. Both Ted, Quentin, and Melissa all know Jeff. He was just instrumental, an operational genius, and seeing to it that this not only got completed, but that it got filled and that it was productive with outstanding cancer care and great revenue. Jeff is just an amazing operator. So along the way, when I became the CEO in 2008, the head of the James Foundation Board said, Michael, you need to think a different way about fundraising. You know, we do the usual cancer ball and, you know, the usual people come and makes us a little money, but we need something else. Do you have any ideas? And I've been thinking about doing a bike event, but I kept it to myself because, you know, the first person you tell it to, you know, you say, hey, I think I want to do a bike event. They go, well, that's a stupid idea. It's dead, right? So, you know, I thought about this and thought about it, say, you know, it's flat. There's nothing like it in Ohio. We've got a great university to help us with this. There'd been a model of it up in Boston. I had talked to the guy who did what's called the Pan Mass Challenge. He gave me some great advice on how to do it better. And so I thought, you know, when Cindy, this woman, said to me, what are you thinking of? I said, well, I have an idea. Can I share it with you? And she said, yeah. And I said, well, the idea is to start a bike event. But instead of a usual bike event, this would be like a really first-class ride. And we would get it paid for by sponsors so that every dollar raised would go to cancer research, no overhead whatsoever. So how much do you think it would cost? I said, well, the planning I've done back of the envelope, it would cost about $2 million a year to do it safely, first class, you know, with gourmet food, masseuses, rock bands. She said, I think I know a sponsor who will do it. And so Cindy Hilsheimer was on the foundation board of NetJets. NetJets funded us for the first year. And between myself, Cindy, and the second in command at NetJets, Danny Rosenthal, we started this bike event called Pelotonia, which is a made-up word like Lollapalooza. And it really took off. First year, we got 2,000 riders. Our business plan called for us to make you know, a certain amount of money in a certain amount of time. We had a board, it was outside of the university. So in the first 13 years, 2009 was the first year we did it in the midst of the last financial crisis. In the first 13 years, the Pelotonic community, which is now it's became the largest bike event in America by riders, with up to 8,000 riders a year. And in the first 13 years, the community has raised over $250 million. 100% of the money goes to cancer research at Ohio State. And now we've just started something with the new Victoria's Secret. Pelotonic Victoria's Secret is giving an award to 5 female cancer researchers at AACR, $100,000 each, and that'll continue to grow as well. So this has been a lot of fun and, of course, had great impact. Ibrutinib, first experiment done in mice, was funded by a Pelotonic grant. Had the opportunity to be the president of AACR, the world's largest cancer research organization, now 50,000 members in 120 countries. And every president gets to do something special. Mine was something called 2020 by 2020. And it was to sequence 2020 African-American cancer genomes along with the normal tissue and get those annotated, sequenced, and uploaded into the database of the National Genome Project. It would be the largest number of African Americans in that project, which is a sad comment. Have undertaken this with Morehouse College of Medicine. We've got about 1,600 patients accrued. Got delayed because of COVID, but now we're back on track. Really, really excited about that. So I had a wonderful time, both mentoring at Roswell and then continued to get mentored by Clara at Ohio State, first coming in as head of Hem-Onc, then the head of the Cancer Center, then the CEO of the hospital. And, but, you know, did that for 10 years. Pelotonia took off, got to be the president of AACR. I mean, just really a phenomenal ride. You know, after a while, you begin to say, okay, well, I've done this. What am I going to do? Just keep doing this until something goes wrong. And we've got a perfect score in the core grant. We're making lots of money in the cancer hospital, a few the cancer center. I've got great people to succeed me. How do we make our next move? And you just realize that I went to see Gordon Gee, and I said, he was a president of the university. I said, Gordon, I want to step down. He said, what are you talking about? I said, I'm done. I've done this. I've done what I can do. You know, he said, well, you want my job? Is that it? I said, no, I don't know what I want to do, but I know it's time for me to step down and let's work on building succession. So I did that and made a little news in our little Scutler newsletter, the Cancer Letter. and really just felt like it was time to recharge my batteries, went into the lab, and found that not to work out as well as I'd hoped. A lot of people still calling me from my board and to do things, and I've been under their direction, and need to give the new leaders a chance to really spread their wings, and especially when you've had this kind of a presence in an organization. So the opportunity, after being in my lab for a bit, and there having been succession, the opportunity came for me to take a position at City of Hope, which is just really kind of what I was looking for at the time. Got much more entrepreneurial at that stage, and really felt like Ohio State, for all the great things that it had, was really, the tech transfer was very, very limited, very small budget. Really couldn't see the sense of moving my NK cell stuff out into a company to bring us further, to get it to the patients. And City of Hope is built on entrepreneurship. Most people don't know that insulin was invented. The process to develop human insulin was invented. Process to develop humanized monoclonal antibodies was invented. All the royalties from Humulin, rituximab, Herceptin, Avastin, all hundreds of millions of dollars a year went to City of Hope. So very, very entrepreneurial, in addition to being an outstanding academic medical center. So I got the opportunity to go there and lead as president. And again, the CEO said, "What do you want to do?" I said, "Well, I've been a CEO. I have your job. I've had your job. Don't want that." So the cancer center is run by my dear friend, Steve Rosen, who was recruiting me. I said, "I don't want that." I said, "I'm interested in growth, culture, and entrepreneurship. I really don't need a position. If I have the opportunity to explore those, I don't know how I'll do, but I'd like to." So, "Well, no, I need you to be the president of my med center, oversee all things clinical, and on our executive board, and really move with us as we start to decide who we are and what we're going to be." We had just acquired TGen, the Translational Genomic Research Institute, but we're looking to just grow from our kind of mom and pop shop in LA to really expand. So that we did. Got there in 2018, and we recruited over another 250 physicians. I was in charge of all the chairs, kind of a dean-like position, or 11 chairs, recruited 8 new department chairs, built or acquired 35 clinical sites in Southern California, put $1 billion into the campus you're looking at right now in Duarte, and then we developed $1 billion new campus in Orange County, about 2 hours closer to the ocean. And then most recently, we've acquired Cancer Treatment Centers of America to help us democratize the care that we're giving and bring clinical trials not only from places like university hospitals and City of Hope and Ohio State, where patients need to come to us, but really bring our trials, export our trials out to community-based centers. And now I think we're the first cancer-focused interstate network of cancer hospitals. So it'll be interesting to see how we're able to develop this. But I'll be transitioning again now at 67 years old, bringing in the next set of leaders, remaining on the executive team, but in an advisory role, and really just focusing on my lab. And I'm just going to end with that. This is my lab. When we first arrived at Ohio State, it started with 2 people at Roswell Park in 1990, and 8 years later we were big, and there's the next year different people, the next year 2013, here we are in 2017, and here we are at City of Hope. As you can see, I want to point out my partner in crime scientifically, Jinhua Yu, is a phenomenal, came with me from Ohio State. Here he's a full professor, NK cell biologist extraordinaire. We have a lot of fun together. So lastly, City of Hope was very interested in our IP portfolio and strongly encouraged us to spin out, actually have equity in the company, and are very, very supportive of it. So we've started a company called Cytomune Therapeutics. We make CAR NK cells, engineered NK cells. That trial you saw going on now in lung cancer at City of Hope. This is the company behind that trial. We built a manufacturing plant in Puerto Rico for a number of reasons. You may not know this, but there are 80 pharma manufacturing plants in Puerto Rico. This is the first cell therapy company on the island. And there's a tremendous talent, tremendous workforce. about 65 employees right now, 35 of which came back to the island from the States to work at Cytomune Therapeutics. So we're very proud of the economic impact that we're having on the community. It's a phenomenal opportunity for us. So with that, I'm going to stop and thank you for your attention. We talked about role of cytokines in NK development. You're now all NK cell aficionados. We talked about where NK cells develop. You now know they develop in secondary lymphoid tissue. Talked about why it's important to know lymphocyte and other forms of development, because from those malignant transformation often occurs and new insights into therapy can evolve. And we talked about clinical applications of NK cells, both in glioblastoma, as well as some of the work we're doing in lung cancer, and as I didn't have time to mention, but pancreatic cancer, AML. And then finally, finish with a few tidbits about my journey as a leader. Have many, many people to thank for that. Most importantly, Clara, but folks like Ted, Technos, and Quentin, and Melissa Childress, who are here, were hugely instrumental, along with many, many other people working as a team together to see us see things through. So with that, I'll thank you for your time. If we have time, I'm happy to take any questions. I've been honored and delighted to be with you today. Thank you.
Thank you, Mike, for that fantastic talk. Any questions in the audience?
Thank you, Dr. Caligiuri, for this wonderful talk, and not only from a scientific perspective, but also about what being a leader means and a mentor, and very, very comprehensive and nice. I'm a thoracic oncologist, and I treat lung cancer patients with certain types of genomic alterations that are notoriously resistant to immunotherapy, right? So patients with EGFR mutations or ALK rearrangements. And do you see adoptive cell therapy having the potential to change the paradigm of patients with actionable alterations that are resistant to checkpoint inhibitor therapy and do not derive benefit from immunotherapy?
So presumably after they've had their targeted therapy and they've relapsed and, we're game's out. I really do. One of the things I like, it's a great question, and thank you for your nice compliments. One of the things I like to remind myself and everyone else is that, we've been doing surgery for 200 years, radiation therapy for 100 years, chemotherapy for about 75 years, targeted therapy for about 20, and immune therapy for about 10. So we are so much in the infancy of this. Take NK cells. Think of how many engineered NK cell trials are out there. Not many at all. But I believe that it is allogeneic. It's off the shelf. So you can literally, it can be at case tomorrow, and you can infuse it the same day. And we've shown you can do that. So there's something there where, compared to the phenomenal results we've seen with CAR T, which, like I said, is about 50% successful when nothing is working. Amazing. We could start thinking about using NK cells differently. First of all, it's a different cell. It releases its granzyme. Its tumor recognition is different. It's not HLA restricted. And it can be used very quickly. Like a patient comes in, there's no need to get anything from the patient other than a consent. I think ultimately cell therapy will become part of the armamentarium, probably, and we are moving towards ALK and EGFR resistant patients into our trial. They have to be resistant to everything else as well. The idea, though, is to move it more and more up front with such therapies so that we can decrease the number of residual cells that are remaining currently with the ALK or EGFR directed therapy. So that's where I really see it going, just part of the armamentarium of anti-tumor therapy. That's where I really see it going. I don't think that any of these by themselves will ultimately result in all patients being cured. There's just too many tumors within one tumor, if you know what I mean. The heterogeneity is vast. But moving it up front for non-cross resistant therapy and immune therapy being part of that is, I think, where this is really going to shine. Thank you for the question.
Mike, this is Kun. Congratulations on a great talk, and No, a very impressive career that I've admired for a long time. NK cells versus T cells. I mean, most of us are more seduced, let's say, by T cells because they persist, they expand, they are there forever. They seem to exert some tumor control. How can you assure that? What do you think in that respect about NK cells? How durable are these responses and thought to be?
Great question, Koen. And likewise, I've very much admired your career and all you've done. So I think the jury is out. Again, like T cells, we've had 10 years to not only see how they do, but to modify them accordingly. And we'll make more and more progress where, CRS diminishes, neurotoxicity diminishes, and efficacy improves. Ultimately, there'll likely be an allogeneic T cell that gets FDA approved at some point. NK cells, as I say, are different. They don't have classical memory. And they need IL-15 to survive the same way granulocytes need G-CSF. So what we've done is we've given them IL-15 so that they can survive longer. But because they don't have long-term memory to the point you're making, you're going to have to give multiple doses of NK cells. It's going to be much more like a chemo regimen. For example, in our trial, we give a weekly infusion for 4 weeks, and we'll be giving up to 1 billion cells per dose of these genetically modified NK cells. In terms of, so you got to, because it is different, we have to think differently about it. They won't be no meaningful number of NK cells will be around months later. That's not going to happen. So, and it also speaks to the point of, will they ultimately by themselves be curable and provide sustainable remissions? I don't know. I think the problem today is that these things are so expensive that the dollars it would take to do the kind of trials we want to do are so enormous that a lot of things may be killed before they get there. Think of the whole, antibody story about how it started not working and then years later Rituxan, and now look. So it takes waves, but because of the expense, my worry is that, we may not be alive or have sufficient funding to really see all the permutations that need to occur with and without other types of therapy. Just as one example, there was a trial in China published in Journal of Clinical Investigation, a randomized trial of 210 patients, randomized to receive, they'd been chemo-refractory to receive PD-1, anti-PD-1 plus off-the-shelf allogeneic NK. And the allogeneic NK arm, much better overall survival, disease-free survival, and overall survival. And further, the patients that had multiple doses did the best. So, if we can get there with performing these kinds of trials, I think we're going to see a place for cell therapy in the long run in cancer, including NK cell therapy and other types, gamma delta T, et cetera. Thanks for the question. Good to see you.
Mike, this is Quentin. I have a question for you as well. So we know CAR T cells are heterogeneous, and you have subsets that are better able to persist, and other subsets that have higher activity. Do you see that for the engineered NK cells as well?
Yes, it's a great question. We know this already. As I started to point out, I apologize for going so quickly through everything. But we have the TRAC NK cell, which is the tumor-reactive NK cell. We have the viral NK cells, and they express different receptors, and certain NK cells see that virus, and other NK cells see that tumor. And it all has to do with the receptors being expressed by NK cell and the ligands being expressed by the if it's a tumor cell or virally infected cell. And so what we're trying to do is to amplify that TRAC NK cell, make PD-L1 positive NK, which we're now able to do with 95% of the cells we're infusing into the patients have PD-L1 highly expressed on their surface, and then combine it with atezo. That won't do anything for viruses, but it is doing something in our preclinical models, and now we'll see if it does anything clinically as well. There's also the CD56 bright NK subset, which lives in the body. It doesn't have granules. It doesn't have CD16. It doesn't have the killer molecules. That's Mother Nature telling you it's not a killer. It's the earliest NK, but it itself is functional. Two things. One, it secretes cytokines, so it's immunomodulatory. And that makes sense because it lives around the parafollicular T cell rich region where those cytokines are needed by other cell types. So monokines, dendritic cells prevent IL-15, activate the bright cells to secrete TNF, gamma interferon, class 2 goes up, et cetera, et cetera. So it's an immune modulator cell, although it's an NK cell. Second, it's plastic. So it can not only become a CD56 dim cell, the killer cell, but it can also become an innate lymphoid cell, ILC1, ILC2, or ILC3. So there are not only further subsets of NK cells, there are other innate lymphoid cells that aren't T cells and aren't B cell, of which there are subsets. And it's kind of like Th1 and Th2. There's ILC1, ILC2, and ILC3. So the story is the jury's not out in terms of understanding lymphocytes and all that they do to protect us from pathogens and malignant transformation.